Hello, I am Zian Hansen. I'm a first-year engineering student here at OSU, and this is for our Physics 211 Project 1. So before I get into the main details of this, with the given equation about this helicopter, there's one major thing about it that I need to put a little disclaimer in before I keep going into the motion diagrams. Is that with this equation, we're given two main components, the first being a component of the x acceleration and the second being a component of the y acceleration. Meaning that you can't do an overall motion diagram with both of them combined. You have to create two separate motion diagrams for the x and its displacement, its velocity and acceleration, and y with its displacement, its velocity and its acceleration. So first, I'll go with the simpler one of the two, the x component. So first, here's our acceleration motion diagram, which is the acceleration in the x direction is equal to negative beta times, use a little thing, times time divided by the constant t, or in the x direction. So as when t is equal to negative t, which is one of the values that we were given in the debrief video, it is equal to negative b. So as time goes from negative t to t, the acceleration decreases, crosses zero, and goes all the way into more of a negative acceleration. And for the velocity of t, or the velocity in the x direction, it is a basic parabola. Since the acceleration was a straight line, this one would make it a curve. So when t is equal to negative t, it starts at zero. Then as time goes on from negative t to t, it goes up, it increases, the velocity peaks at when t is equal to zero. It comes back down, so it back to zero at t. Then for the position of x, it's a little more confusing, but when t is negative, it starts relative to the origin of the graphs, which is at when time is zero. It starts in behind the origin, and as time goes on, it becomes positive. It goes up through the origin, passes beyond the point into a more positive location compared to the origin. Then for the acceleration of y, first, the acceleration starts positive. Then as it goes from negative t to t, goes acceleration becomes negative, then comes back up to zero, then it goes positive again, then it goes back down to zero. This is not symmetrical. No, but close enough. Then for velocity of y, it starts at zero when t is negative, when little t is equal to negative big T. And as you go from negative t to t, the velocity goes up, it goes back to zero, then it goes up again for a little bit, and it returns to zero at t. And for the position of y, it starts positively. So then it slowly floats down as it goes towards the surface. It hits the base or origin, which would be the ground level, and it rises back up as you approach t.
Is it still recording? Mm-hmm. And we're back. All right, my name is Sjoerd. I'm also a first year here at OSU, and I am currently a computer science major. So I'm going to be talking about the sense making of the situation and the results. And I'll be explaining and making sense of both the situation and the results shown in the video. In doing so, I will explain both the physical representation of the motion and its independence or dependence on each of the given variables. To start, I will reason why the acquired results are what they are. The equation is simply based on integrations. We were given the acceleration function, but needed velocity and distance functions. So through a process of integration and double integration, we were able to find the required functions, where the integration of the acceleration function results in velocity function, and the integration of the velocity function results in the position function. Using those, we were able to sub in the info we knew, using t is equal to the negative big T and initial velocity I is equal to zero to find the time and distance. To put this in a physical representation, the equation can be separated into x and y components, or horizontal and vertical components. The equation already does this by separating x hat from y hat. To see this as a physical representation, we must think about what the question is asking. Considering the question is in regards to helicopter flight, it would be logical in a physical representation to use x hat to represent the horizontal distance covered by the helicopter as a function of time, and the y hat to represent the vertical distance covered by the helicopter as a function of time and the y hat. as a function of time. So on the slide, you can see the helicopter going up or using y hat as the vertical distance, and then x as a horizontal distance, with a small d representing the total distance covered, and then t equal negative big T and t equals big T to show the starting and ending times. Another important part of sense making is the justification and verification of units. If my slide would move, there we go. However, the video is solved fully symbolically, leaving us unitless for the alpha and beta constants. The video does give us the final time equation, where t is equal to the square root of 3/2 times d over b. Solving that gives us beta in meters per second squared, which when plugged into both the velocity function and distance function cancel out with the seconds to get meters per second and meters respectively. And that can be seen on the slides. On the left-hand side, you get the velocity of time function with the given function that was in the video written out to show the units, and then kind of equating to see that the units are equal. And on the right-hand side, you have the same thing, but for the position function, and you can see that meters is equal to meters. Furthermore, it's important to talk about the dependence of the results on the variables in the equation. Alpha and beta are both constants, meaning that they are unchangeable and will impact the equation in the same manner each time. However, the t and big T variables do impact the final results of time and distance traveled. With the rest of the equation constants, then increasing the starting t would decrease the distance between initial and final t as less net time is traveled, which also shows that there's less time in the air. Although x hat and y hat are still prevalent in this equation, they are not variables, more so indicators of direction that make the functions vector functions. Thank you.
All right, my name is Zayden Bradbury. I'm a first-year engineering student. Now we're going to be looking at the reflection, which is basically the similarities and differences between the problem we've seen in Paul's explanation and the problems we've done in class. So I have pulled up the dragon boat problem we did in lecture in week 2. And the dragon boat, you can see, is similar with the function of acceleration with respect to t, and the function has a big T and little t variable, much like we did in this problem. Yeah, so it includes that known constant t, and there's similar goals for finding the time and finding the change in distance. We are looking at finding out how much time it takes the boat to return to its initial velocity and finding out the position of the boat at that time, which is really similar to our main goals for the helicopter problem. There's a main difference, though. The difference is that we are only looking at the x direction for this one, while in the helicopter problem, we had both an x and y direction vector, and we don't have known constants alpha and beta as well. We just have our known constant t in this problem. But this problem is really similar, and we can see that we have the acceleration graph here, which is super similar to the one we graphed. And we determined that the function for, or that the constant beta, we determined the units was a unit of acceleration. So starting at the initial acceleration, it makes sense for this problem as it goes closer to t. And for both of these, we can see that they are a real world context problem. We're using both the same 1, 2, 3 steps to understand a plan, and we're calculating the unknown quantity, first solving it symbolically, which Paul did in the video, and then we're plugging in numbers. Makes sense, but we just solved this one symbolically, but we could plug in numbers to get a better representation of that as well. And now we made sense of our solution by verifying the units and making sure that graphing it and representing it in a diagram made sense with the problem itself, because if it didn't, then we wouldn't really be sense making the solution. I think that is it.